I'm going to describe an analytic approximation scheme for the Dirichlet problem, a scheme that I've only recently found in the literature. My curiosity was further aroused because while Maple can solve some elliptic boundary value problems analytically, it doesn't have a numeric solver for such problems. I found the algorithm in the 1964 Benster translation of the Kantorovich and Krylov text, Approximate Methods of Higher Analysis. That's a text from the 1930s. Now, Table 1, the summary there, assumes that the elliptic operator is Laplacian. And here's what the algorithm requires. Let U sub k be an infinite set of harmonic functions. Any harmonic functions, no special properties imposed. Parameterize the boundary via arc length S. Let f of s, that's this function here, be the value that the solution assumes on the boundary. Evaluate each of these uk's on the boundary and let phi k be the function that results, phi k of s. Orthonormalize those phi k's and call the orthonormal set so obtained psi k. Expand the boundary function f in terms of these psi k's and let the coefficients of that expansion be called ak. And then you write the sum ak uk, that's the approximate solution. Well, at great cost, Kantorovich and Krylov give a two-term solution to example 1, which we'll see momentarily, and we'll implement that solution in Maple to illustrate the process that we've described in Table 1, and it will also demonstrate Maple's computational efficiencies. Okay, so what's this example 1 that we found in Kantorovich and Krylov? So here's the boundary value problem. Laplace's equation on a square. Square is centered at the origin. The corners here, minus 1, 1, minus 1, 1. So square has side 2. Boundary data, left side, right side, 1 minus y squared. Top, bottom, 1 minus x squared. Well, Maple can provide an exact solution to this problem, but the square has to be placed in the first quadrant. So that means some shifting. So the edge values become, in terms of alpha and beta, the new coordinates. Here are the transformations that you have to apply, just a linear shift. Boundary data. Here is Laplace's equation. Invoke pdsolve command. The equation is labeled with Q. Here are the boundary conditions. Here is Maple's solution. Translate back to x and y. The solution looks like this. We want to draw some graphs and do some computations. So instead of summing to infinity, we'll try 10. So this is what a 10-term exact solution looks like. Draw some graphs. This is a graph of, I call this U10. This is a graph of U10. Then I looked at the edges. So here is one edge, took 1 minus x squared and compared the edge value of this approximation. Draw the graph. Graphically, it looks bang on. Now, Kantorovich and Krylov claim that at the origin, the value of the exact solution should be 0.816. If we evaluate U10 at the origin, we get 0.821. And I even tried with 20 terms, U20, I get the same number. So U10 seems to be pretty good to take as the exact solution. So let's look at this Kantorovich and Krylov approximate solution. We need some harmonic functions. So I'll make use of some Maple here, student vector calculus package, PD solve the Laplacian. You get, as a general solution, arbitrary functions of y minus ix and y plus ix. So I took polynomials with argument y plus ix. So I have a sequence of the real parts, y plus ix, and a sequence of the imaginary parts. Now the very first imaginary part is 0, so I remove that, and you can see that the functions that I've generated, here is a degree 0 function, constant, 2 degree 1 polynomials, 2 degree 2 polynomials, 2 degree 3 polynomials, and so forth. So I just fill the screen with these. Then I call this whole collection by the name phi, so I can reference phi 1, phi 2, phi 3 by pulling them out of this list. Next, we need to do the Gram-Schmidt orthonormalization. Now, I'm orthonormalizing these functions, not their values on the boundary, because in the path in command that it takes to do the orthonormalization, that command will evaluate these functions on the boundary. So the Gram-Schmidt orthonormalization process can be implemented in Maple. Line segments, just define the nodes. The last one is the first one, so we complete the path around. And Gram-Schmidt, do the first one, function over its norm. And to get its norm, use the path in command, apply it to phi 1 squared. C is the appropriate syntax for the path in command. Do that. I didn't want to do counting, so I said, okay, Maple, you tell me how many things there are in this list. And then for each additional function, you just do Gram-Schmidt. You subtract off the component that you have previously found using, again, the path in command. Phi k is the kth member of this list. Here is the previous orthonormal function. Then normalize. So this produced this list of psi k. Next, we need to expand the boundary data in terms of these psi k. Well, on each edge of the square, the boundary function is different, so I have to do each edge separately. So the determination of the coefficients A are going to require integration along each edge separately. So that's why there's a repeated path int. So here it's 1 minus x squared against psi k, 1 minus y squared, 1 minus x squared, 1 minus y squared, as you go around the 4 edges of the square. And what happens is you get this list of coefficients, a lot of zeros. Now, Kantorovich and Krylov got rid of a lot of their zeros by invoking the symmetry in the problem. I just said, Maple could handle this. Let's see what happens. And so these two non-zero terms here are what Kantorovich and Krylov were dealing with. And I just went out to the next one. So I want to see what one more term would do. So there are two approximations I'm going to look at. The one that Kantorovich and Krylov used, the two-term, and KK was already in my head as the abbreviation for Kantorovich and Krylov, but two terms and two k's, that worked okay. And then I used three k's. Okay, uh, here's what they look like. Two terms, Kantorovich and Krylov. Three terms just to see what happens if you do one more term. Finally, we want to test the accuracy of these approximations. I mean, anything is an approximation to anything else. It's just a question of how accurate is the approximation. Okay, so how did I test the accuracy? So here I look at the two term, here I look at the three term, I look on the edge. For the two term, well, it's close, but it's not perfect. The three term is really good. Okay, then I graphed the surfaces, the solution surfaces. So what I call the exact solution, U10, in green, and the two-term approximation, Kantorovich and Krylov, in red, and they look pretty good graphically. And here's the three-term, same color scheme, and it looks pretty good. So analytically, how could we compare? Absolute value of the difference, two-term here. Seems that in the corners there are these spikes. They go up maybe no more than 0.5, okay? And for the three term, no more than maybe 0.11, something like that. That's graphic. What about looking analytically at this difference? So let's see if Maple's optimization tools can find where this difference is the most, and the greatest difference that it finds for the two-term approximation is 0.46 maybe, and it says it's in one of the corners. And for the three-term approximation, it's 0.11, and it's near one of the corners. This is precisely what Kantorovich and Krylov write as their two-term approximation. It has y4th here, and they have this strange mixture of exact fraction here, decimal here. See, they did a lot of rounding to 3 or 4 places. They didn't have the tools like you have in Maple. So again, they test their approximation at their approximation at the origin, and they get 0.814, and claim that the exact value should be 0.816. But I found that the exact solution at the origin is 0.821, and these Maple generated solutions, the two-term and the three-term, evaluate at the origin to 0.822 maybe, and 0.821. Okay, so working in Maple was a lot more accurate than working with pencil and paper, the way Kantorovich and Krylov were forced to do. I took a second problem, Dirichlet problem, on the ellipse. So here was my boundary value problem that I set up. Took an ellipse. It goes this way. How did I begin? I began with a solution. Here's a harmonic function. On the boundary of this ellipse, these are the boundary values. So this is what this function looks like. So this is what our solution should look like. And on the edge, this is what the graph of the edge condition would be. And where did I come up with this? Took the imaginary part of this linear fractional transformation, and I evaluated it on the ellipse. Then I applied the Kantorovich and Krylov approximation technique. So I would have a solution, an exact solution to the problem that I was building an approximation to. To solve this, I did some initialization steps here, working in Maple. Okay, student vector calculus. Here is where I got my function v from. It is indeed a harmonic function. create the list of functions. Phi, same way. And the path, Maple's path in command understands what an ellipse is, so define the syntax for that ellipse. Next is Gram-Schmidt orthonormalization. The code is essentially the same. The results here now show up with floating point coefficients. Y floats. Well, if you look right here, you'll see this decimal. That tells Maple's path in command that it should kick over into numeric evaluations. And that makes sense because I'm integrating around a boundary of an ellipse. And if you do it exactly, you get elliptic functions, and the expression swell is tremendous. So here are the psi k's. Now we need to expand the boundary function in terms of the psi k's. The computations are the same, only we have to take care of round off. So here's the list of the coefficients. A, you'll see some zeros interspersed amongst the non-zero ones. We form a sum, AK psi k. So this is what our approximate solution looks like. And then we want to test the accuracy of these approximations. Again, graphically, red and green are interspersed. Here is the difference between the exact and the approximate on the order of 5 thousandths. Here is what happens if you look on the boundary. It seems to spike here at pi. Here's a graph of a comparison of the boundary values. And here is an analytic evaluation of the difference. Take the inf norm because it can be parametrized by theta. And it's on the order of 7 1,000ths. So you can see here on the order of 7 1,000ths. The worst error you make, and you make it on the boundary. So for relatively little effort, using Maple, of course, you can get a pretty accurate approximation of the solution of Dirichlet problem. I did do a couple of other examples, but we don't have time to look at them here. A third example that I did was Dirichlet problem on a triangle. And a fourth one was Dirichlet problem on a region bounded by two arcs. The two arcs are cos and sine. It kind of looks like a banana. Swoop this way and swoop that way. And the outcome is pretty much the same. Good approximations. The work is essentially the same. Maple does all the calculations. And I was amazed at the outcome here to discover that there was this approximation technique that I had never seen before anyplace else. And I don't see it discussed even now. I guess it's all gone to digital. But it was fun.